Okay, let's dive right into this. Welcome to today's explainer, where we're going to totally demystify what is arguably one of the most maddening problems you can hit on your test bench, a newly rebuilt Rexroth servo motor that is just shaking violently. I'm incredibly excited to guide you through this today. Because look, we aren't just going to list off which buttons to press in the software, we're going to actually unpack the fascinating engineering theory that makes these motors tick. By the end of this explainer, you're going to understand exactly how to align and fix this issue using field-oriented control principles right inside Rexroth's IndraWorks software.
Picture this for a second. You've just spent hours, literally hours, carefully overhauling a Rexroth servo motor. And you did everything right, you know? You swapped in high-grade bearings, you perfectly mounted a brand new Sick Stegmann SKS36 encoder, you bolted the whole shebang back together with absolute care. You're ready for the payoff. But then you power it up to run a simple test, and the motor just refuses to spin smoothly. Instead, it vibrates violently. It makes this heavy, terrifying mechanical grinding noise, or it just immediately trips the drive, flashing a fault code right there on your IndraWorks screen. It's an incredibly frustrating reality. But hey, take a deep breath. I really want to reassure you right out of the gate. Your mechanical assembly, it's likely absolutely flawless. You didn't mess up the rebuild. The core of this mystery is actually surprisingly simple. The drive is currently completely blind to the motor's magnetic poles. Without the proper calibration, the drive simply cannot see the internal magnetic fields that it needs to spin that rotor smoothly. So to understand why this happens, and more importantly, how we fix it, we've got to look past the physical hardware on the bench and explore the really elegant mathematics running the whole show. Section 1. Unseen Forces. Exploring Field-Oriented Control Theory. So the Rexroth IndraDrive handles its complex tasks using field-oriented control, or FOC. Now, in a permanent magnet synchronous motor, trying to manage three-phase AEC currents, IA, IB, and IC, is mathematically a massive headache. It's incredibly complex. So the drive actually uses a brilliant mathematical trick. It uses the Park and Clark transformations. These transformations basically grab those three complicated phases and boil them down into a highly manageable two-axis rotating reference frame. It's like simplifying a giant 3D puzzle down to a flat 2D map. Now, those two mathematical axes, they're the D-axis and the Q-axis, and man, they are completely different beasts. The D-axis, which stands for the direct axis, runs perfectly parallel to the rotor's magnetic flux lines. If the drive sends current there, it basically creates a magnetic field that pushes directly into or away from the permanent magnets. The result? Absolutely zero torque. None. All it does is create unwanted heat and a ton of magnetic stress. But on the flip side, the Q-axis, or quadrature axis, sits exactly 90 electrical degrees perpendicular to that rotor flux. When current gets injected into the Q-axis, boom, you get maximum electromagnetic torque. It is literally the axis of pure power. And this brilliantly illustrates the fundamental torque equation for an ideal surface mount permanent magnet motor. T equals 3/2 times P times psi sub m times I sub Q. Let's break that down real quick. P represents your pole pairs, psi sub m is the permanent magnet flux linkage, and I sub Q is your quadrature current. What this equation is screaming at us is that to maximize the efficiency and the dynamic response of your system, the drive absolutely has to keep the D-axis current exactly at zero. It needs 100% of that vector current directed exclusively into the Q-axis. Which brings us to Section 2, the mathematical culprit, misalignment. So what's causing the shaking? It's a domino effect of misalignment. Remember, the drive doesn't physically have eyes. It can't see the rotor magnets. It's calculating the positions of the D and Q axes purely based on the absolute angular feedback it's getting from your brand new SKS36 encoder. But here's the catch. When you bolted that new encoder on, its physical mounting position inherently introduced a mechanical offset relative to the true rotor flux vector. If your encoder alignment is mechanically off by, let's say, 30 electrical degrees, the drive thinks it's injecting current purely into the Q axis. But because of that offset, a massive chunk of that current bleeds directly over into the D-axis. Torque control is instantly lost. The velocity loop completely breaks down, your current regulators saturate, and the entire system enters this wild high-frequency mechanical oscillation as it desperately hunts for equilibrium. And that right there, that is the violent shaking you're seeing on your test bench.
Let's move to Section 3, the IndraWorks interrogation, locking the poles.
So the crucial point is following these exact calibration steps inside Rexroth IndraWorks to fix this. Step 1 is overcoming bearing stiffness. Think about it. You've got brand new high-grade bearings, super tight seals, meaning the motor has high static friction, or breakaway torque. If you don't give it enough juice, it literally won't be able to physically align itself. So you need to go straight to parameter P-0-0518, that's the commutation current, and crank it up to 100% of nominal current. Step 2 is triggering the actual alignment. Navigate over to parameter P-0-0522. When you execute this command, the drive energizes the U phase and V phase, creating this massive fixed magnetic lock. On your bench, you are actually going to see and hear the motor shaft physically snap into place and hold completely stiff. At that moment, the rotor is perfectly locked to the stator's magnetic field.
When that physical snap happens, the drive instantly reads the position from the encoder and calculates the exact angular offset value. It then temporarily saves this value into parameter P-0-0521. This number is the literal mathematical anchor, guys. It is the exact angular error correction factor that shifts the drive's mathematical coordinate system, fixing those Park and Clark transformations we talked about so that they now perfectly match the real physical axes of your newly rebuilt motor.
But hold on, there is a fatal trap right here. And honestly, this is where most engineers make a really heartbreaking mistake. The value sitting in P-0-0521 right now, it's only saved temporarily in the volatile RAM. If you were to turn off the power right now to, say, go grab a well-deserved coffee, the drive will completely forget this number, and you're going to be right back to square one with a violently shaking motor. You absolutely must permanently store that commutation offset into the data memory of the SKS36 encoder itself. To pull that off, you always have to execute command P-0-0524 or use the C1100 copy command. Oh, and pro tip, always power cycle your drive afterwards just to definitively verify that the value stayed locked in perfectly.
Section 4, the proof and cost savings.
Now, what's really interesting here is the actual torque metric you get to see at the end of all this. If you pull up the IndraWorks status monitor while running your newly aligned motor at, say, 20% speed, you're going to see it start up instantly, no hand assistance needed. It's going to run completely smooth, completely silent. And that actual rusting torque, it'll sit beautifully right there in the single digits, usually around 4 to 5%. This is exactly where the torque should be for a healthy, no-load motor. It proves the D-axis current is back to a perfect zero, and that Q-axis is doing its job flawlessly.
Which leaves us with one final, pretty amazing thought. By understanding the field-oriented control theory today and mastering this parameter-driven calibration process, you just avoided massive OEM replacement costs. You completely bypassed those frustrating third-party repair timelines that, let's be honest, often come with zero warranties. So how much time and how much money can you save your facility by mastering this elegant mathematical principle right there in-house? It's a pretty empowering thought, isn't it? Thank you so much for joining me on this explainer. I really hope this deeper understanding of servo motor commutation serves you incredibly well on your very next rebuild.